Let me start with a question that we had been discussing primarily three-dimensional situation where the picture was that I input at large scales L and I have this energy cascade down to small scales where it gets dissipated at some scale LD, and the rate of dissipation equals rate of injection equal to transfer rate. And so that epsilon, this is a player all the way through. And so far as these scaling arguments go, I'm interested in the scaling of this so-called energy spectrum. We have done enough discussion on the velocity increments, which are essentially at the heart of turbulence. So we have seen a lot of manipulations with that. But then, I mean, back to things which are much more straightforward, and what one talks about a lot is the so-called energy spectrum. And energy spectrum is defined as the total energy resolved into the spectral decomposition. So in the wave vector space, written as EK dk, this is your usual 1 over 2v v square d3r. So the average energy written as this, and EK is this universal behavior is that EK determined by epsilon and K alone. I said that EK is equal to some constant times epsilon, where dimensional analysis would give me this. I didn't work it out, but have you worked it out? That's the first question. Have all of you done the little bit of exercise to see that this is k to the power minus 5/3? No. I mean, these things are meant to be, this is a school, so one is supposed to do the homework also, right? So the dimension, so let's say the only dimensions available to us, mass is out, so it's L, the length and time. So E, dimension of E is L square over T square, right? Is that? So what's the dimension of EK? Pardon? L cubed by T square. So EK is going to be L cubed by T square. So that I'm claiming is determined by epsilon, let's say epsilon to the power x, and k to the power minus y. So let's say k to the power minus y. So the dimension of epsilon, what's the dimension of epsilon? That's the rate of transfer, the rate of dissipation, everything. It's whatever you can talk about with energy, it's that. So what's the dimension of epsilon? L squared by T cubed, good. So epsilon is L squared by T cubed, and K is of course 1 over L. So L cubed by T squared is equal to L squared over T cubed to the power X, L to the power Y. So immediately X is equal to 2 by 3 and Y is equal to 3 minus 2X is equal to 5 by 3. So that's how you get it, right? So the Kolmogorov 5/3 law is a pure and simple dimensional analysis, and this is how you get the thing. Now when it came to d equal to 2, I said that there is input over here, and this is the direction in which entropy, which is omega square, so that flows, and the energy over in this case, so this is D equal to 2, and energy flows backwards. So if I once again look at E of k is going to be determined once again in this region of wave numbers. So wave numbers greater than the input wave numbers, there it would be determined by the energy transport and by the energy transfer rate. And so what would be the dependence of E of k on k? So if for this backward energy cascade, E of k is determined entirely by the energy flux, which is epsilon, and k. So what should be the k dependence of the energy spectrum E of k? K? 5/3. Right. So k to the power minus 5/3. The different one would be when you are doing the energy spectrum in the forward direction, where it is determined by the entropy flux, which is ES. And that was the other thing that you were supposed to find out. So it is some number times epsilon s to the power something and k to the power something. So anyone who has an answer to that? Pardon? K raised to the power minus 3 and epsilon s raised to the power? Pardon? 2 by? So epsilon s to the power 2 by 3, k to the power minus 3. So big difference between this and this. So that's something which, and finally I had said that there is this rotation, the rotation in d equal to 3, and that I had said that sort of two-dimensionalizes, but not in the way you would want, like it, that, I mean, it is all taking place, it's a two-dimensional velocity vector in a 2D plane. That's not the way it works. It changes the energy spectrum. It's no longer minus 5 by 3, and I had said that there is this helicity, which is V omega dotted with V, which is another conserved quantity in the inviscid limit. And so the energy spectrum, if you look at it now, here is the injection, and energy, this is a little bit which I have not done at all. Energy can flow both backward and forward, and helicity flows forward. So helicity flows forward, and the spectrum now is determined, E of k is determined by helicity flux and energy. So they determine the, and that you can sort of try it out, that what would be, this is the last bit which I had talked about yesterday, that E of k is going to be epsilon to some power y, and h, which is the helicity rate, let me call it dh dot, so the rate of helicity transferred to the power y, and k to the power, let's say, minus m. So as an exercise, do x, y in terms of m, and you should be able to conclude that m has to be less than 7 by 3. That's the bound which was found by Shagor some 9 years ago. and which is respected bound. So this is how the dimensional analysis proceeds. Very different, I mean, from what we have been discussing at the all this is just, I mean, a lot of power counting gives you power counting with the physics. See, the physics was easy over here, which we spent a lot of time talking about. And it is sort of, once again, d equal to 2 extra conserved quantity. And you have two different kinds of fluxes. There is a difficult bit of physics over here, which you should, that's the part which I did not talk about, that there are these two things which can cascade, and how do I argue that this goes forward and this goes backward? That's something which would be, this is known as Fjordhoff theorem. This is something which you can do the background reading on. And over here, the fact that energy goes both backwards and forwards, and H goes forward, is once again a variation on this the Fjordhoff theorem, and that's the physics part of it. After getting the physics right, you can do these pure dimensional analysis and get feeling for what sort of answers you should get in the real world without worrying about the intricacies of anomalies and whatnot, which drives the subject. So there are two, I mean, essentially what I'm after, there are two levels at which you can understand things. The first couple of days when we did the real calculations, there it was a question of trying to understand what drives it, why is it a difficult subject? And so the intermittency, which makes it difficult and unsolvable, is also a very small effect, and not d equal to 3, it becomes prominent for the high moments, but not for this. D equal to 2, intermittency is hardly there. And but it goes to the heart of the subject. So it's important to know why and how. But then, I mean, you can merrily ignore these effects, do dimensional analysis, and get a lot of answers. So that's what, I mean, for the next couple of days, that's exactly what we will be doing. And to set the stage for that, let me go back and let me start with this question of Navier-Stokes equation once again, and talk about, I'll drop the pressure term because I'll do a scaling analysis. The pressure term would scale in the same way as this term. So I'm dropping the scalar term, but just like sort of Banco's ghost, keep a bracket over there. And then nu del square V. So I want to look at how does the scale invariance of this, scale invariance of Navier-Stokes equation. So what's meant by scale invariance? The scale invariance means that I will go from x to some x prime. I will scale x by a length L and talk about some x prime, which is sort of dimensionless. I have scaled x by length scale L. So x is equal to x prime times L. So now as I scale the length scale, t would also have to be scaled appropriately, and this is by some L to some power z, which you don't know as yet. So t is equal to t prime times L by into L by z, L to the power z. V then is V prime L to the power 1 minus z, and we are ready to, and what do we want? Scale invariance means in the primed variables, same form. So that's what the scale invariance is all about. So del V, del T. So what does the first term become? Del V prime, del T prime, and this is L to the power 1 minus 2Z, plus V prime dot gradient prime V prime L to the power Hmm? 1 minus 2Z, right? So 1 minus 2Z equals that plus nu, and so it is now L to the power, there is 1 minus Z, and there is L, so it's minus 2, right? And 1 minus Z minus 2 del prime square V prime, right? So this is the way things are. So what happened? Yeah, all right. So, so this is minus 1 minus Z and this. So this is supposed to be scale invariant. So let me write the next step. Del V prime, del T prime, V dot grad V prime is this plus nu L to the power. Now it is minus 1 minus Z, which brings in, so minus 1, so it is minus 2, and it is plus Z times nu del prime square V prime, right? Sorry, Z. Yeah? Correct? So these two, the original equation which I have over here and the primed thing would be exactly equal, would be exactly similar if Z is taken to be 2. So Z equal to 2 for scale invariance of Navier-Stokes equation, which exactly makes sense because it's a diffusive equation apart from this term, which is Galilean invariant and really a part of the total acceleration. It's a diffusive equation, and therefore T has to behave like L square. So if in what time does momentum diffuse over a region of size L, the time is going to be of the order of L square. So that's what diffusion tells you. That's what the diffusion equation tells you. That's what Z equal to 2 has told you. And therefore, everything is according to your expectation. However, when it is this turbulent Navier-Stokes equation, I have an extra constraint. Constraint is that energy transfer rate, epsilon, the energy, everything, transfer rate, dissipation rate, injection rate, but it is scale independent. This is an added so epsilon is scale independent. That's an additional constraint that turbulence puts on you. So epsilon, therefore, but what's the scale of epsilon? I have written it down over there, which is L. So if I were to rescale, so epsilon is going to be epsilon prime L to the power 2 minus 3Z, right? Because that's the definition. I mean, the dimensions of epsilon are written down over there, L square over T cubed, as you can see. So epsilon and epsilon prime are related by this over here. And if epsilon is scale independent, that's epsilon and epsilon prime are the same, then require z equal to 2 by 3. Correct? So z equal to 2 by 3, if this is scale independent. So now what happened to Navier-Stokes equation? I have a problem over here, that this then is not scale invariant. Well, it becomes scale invariant if you assume that, so Navier-Stokes becomes scale invariant if nu is scale dependent. So if nu is scale dependent, that's when Navier-Stokes equation is going to be scale invariant, provided I define nu prime to be defined a nu prime, which is nu times L to the power minus 2 plus z. Z is 2 by 3, which is minus 4 by 3. So nu has a scale dependence which goes as 4 by 3. So what this implies for the scale invariance of Navier-Stokes equation, the viscosity, kinematic viscosity has to acquire a scale, and that scale has to be like L to the power 4 by 3. Does all these things, do these things make sense? Absolute physical sense, because the time scale for diffusion, which was T like L square, has now become T L to the power 2 by 3, which means that to spread over a distance L, here it is momentum spreading. It could be it would be when if it is heat being transported, as we will in a few minutes, or it's particles being it would be the same type of scaling, that instead of L square, you have L to the power 2 by 3, which means that you are diffusing out much faster, right? I mean, the whole business of stirring your sugar in the coffee was that you want it to diffuse faster. And that's what you are seeing over here, that the time scale, the time scale for the thing to spread over a distance L has now become L to the power 2 by 3. So instead of the L square which you had over there, it's L to the power 2 by 3, and the price, and at the diffusion coefficient, which is this viscosity, diffusion of momentum, the point is that the viscous coefficient, this diffusion coefficient is scale independent and increases with scale. So you have a scale-dependent diffusion coefficient, making the diffusion coefficient larger at larger scales, make the process diffuse much faster than it would have without the turbulence, and therefore the mixing which turbulence has. Why what you were seeing in this first slide that Rama showed yesterday, that many people like turbulence because it's a mixing process. You do too, I mean, when you want to stir your sugar. So this is it. I mean, this is how these things work. It's a scaling way. And now the fact that this Z has to go to 2 by 3, it has more, apart from making certain issues clear, it also has to, it's the issue which a whole lot of literature in which the primary player is Krishnan, and then there were various kinds of bifurcations along the way. All of this depends entirely, this part of literature, which is doing calculations in momentum space, has to do with the fact that this time scale is given by L to the power 2 by 3, and that essentially forms the cornerstone of many activities in this area. So, so this is, I mean, this is sort of completely ignoring the processes, the anomalies, and so on, which we had talked about for the last couple of days. You can be blind to it and yet do things with the picture that I have a scale-independent transfer rate. That you cannot avoid. That is at the heart of turbulence, that there is this rate of injection, which is the rate of dissipation, which is the transfer rate. That you cannot avoid, and therefore, I mean, that's there. But that puts this strange constraint on the scale invariance of Navier-Stokes equation, and as soon as you use that constraint in the scale invariance, you see a set of physical results and also a set of results which helps the calculation procedures of a certain kind. So this is it, right? I mean, so, clear? Huh? Yeah? Pardon? Huh? We are just saying that epsilon is scale independent. That would have simply told me that this would be a nu prime such that nu prime is equal to nu L to the power minus 2 plus Z. That's what I could have written, but I could not have fixed the Z. So that's what I did. I mean, right? I mean, but the dimension analysis of what? The only physical input is scale independent epsilon. Yeah. No. 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 Dimension of viscosity has nothing to do with this at all. I've never used the dimension of viscosity is L square over T. It's diffusion L square over T. Doesn't tell me anything about what's going to happen. But that would not fix my Z. Yeah. Yeah. I mean, it does not, no, why should I, where is L square over T? I mean, this is it. That's the point. In nu prime, this has dimension of L square over T. This also, I mean, has physical dimensions of L square over T. But the point is that this is, I mean, that is, if the scale dependent, if you were to write down the scale dependent viscosity, viscosity does have a dimension of L square over T. That is certainly there, but now the point is that this is this turbulent viscosity. It would be, nu would be determined by epsilon and K or L, which is the scale, and nu is equal to epsilon to the power 1/3, L to the power 2/3. That's the dimensional analysis of the viscosity. It's the epsilon has to enter, because it's the epsilon which is driving the viscosity. So if I want to do a dimensional analysis on the viscosity itself, I would do that. I would have to take into account that it's epsilon which is the driver, and do a dimensional analysis on the viscosity, saying that it depends on epsilon and L. And then I would get epsilon to the power 1/3 and L to the power 2/3. That the epsilon to the power 1/3 does not come from the argument that I gave you right now. But yeah, to get that, I would have to, I mean, keep, yeah. Yeah, go ahead. Because, I mean, that is the Kolmogorov picture. That it's epsilon flowing constantly through all scales, so it's scale independent. So I'm imposing the Kolmogorov picture of turbulence through this single statement. Yeah. Pardon? Yeah. Yeah. Right. So this is it. I mean, this is the scaling of the eddy viscosity. If you took the Reynolds stress and expressed it in terms of the used it to define an effective viscosity, then that would be your eddy viscosity. And if you now ask the question that in a Kolmogorov kind of situation, what would be the scale dependence of the eddy viscosity, then this would be the answer. So what is the physical viscosity that we are talking about over here? That is the eddy viscosity that you are talking about, which would go into all these K epsilon models and what have you, which you have for effective models of they use scale dependent viscosities, and the origin comes from here. Yeah. Right, so now I'm going to change the system completely. So enough on this kind of problems, and it's time to look into something which is quite different. Techniques will remain the same. It would all be some understanding of the physics and some scaling arguments, but with now a completely different system. Turbulence, but turbulence induced now in a very different fashion. The system is going to be a layer of fluid separate between two infinite parallel plates. Infinite, not infinite obviously, but some distance L over here such that L over D, the so-called aspect ratio, is much greater than 1. In all that we are going to say and do, the aspect ratio would not come in, so much simplified. So I'm not even bothering. I'm just saying that they are infinite parallel plates separated by a distance d. All of you who have physics background have seen capacitors with this kind of a geometry, and nobody asks you what was the area of the plate, so who cares, right? So and I'm going to maintain a temperature difference between the top plate and the bottom plate. The plates are perfect conductors, and so there is no question of heat flux across the plates. So there is going to be, this is going to be this question of, that is, these would be equitemperatures. So perfect conductors, so you have a constant temperature on the plate everywhere. So this is at T1, this is at T2. If T1 is greater than T2, then you have unstable stratification. And if T1 is less than T2, you have a stable stratification. Our distance d would be small enough for something, 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 which I'll complete. To my advantage. So, and what I'll try to do, so this is delta t. Delta t is equal to T1 minus T2. That's the convention one everybody uses, bottom plate minus top plate. And I'll increase the value of delta t, whether heated from above or heated from below, and ask what happens to the flow pattern. How is turbulence generated in this system over here? So this is the primary question. In a stratified fluid layer, I want to talk about Kolmogorov and so on and so forth. So this is the geometry. Then one can generalize this to rotating plates. So you rotate the plates with, so it becomes a laboratory for the atmospheric flow. And then you can generalize it still further to have charged fluid and have a rotation and also put an external magnetic field. So that becomes the laboratory for flow in the mantle of the Earth. So this is atmospheric flows. So a laboratory for various kinds of games. So this is a very nice system to discuss. It is a sort of lab model for very complicated things. All right, so what's going to happen? What's going to happen is that if I start with this T1 greater than T2, then if the temperature difference is small, so delta T small, then there is only conduction of heat. So heat will transfer from bottom plate to top plate only by conduction. If delta T is raised to a critical value, that's when convection will set in. Now, this is something which yesterday you were hearing about, linear stability analysis and so on. And you see these, what will be the picture is that there would be these conduction rolls which would be formed. This is a very idealized situation where if it's a three-dimensional box, and if you look from the top, the plan form would just be a set of straight lines. That's not reality. This is, I mean, the theorist's simplification. If you look at the plan form, really, they are, in most cases, a set of hexagons, which you must have seen if you boiled water with spices in it, and then if the water evaporates on the fry pan, the pattern that is left behind is sort of broken hexagons. So this is it. I mean, that's the convective rolls. So now, when does this state go over to that state? Well, it is controlled. Who wants to transfer this to that? So you want this hot air to rise and the cold air to fall. The rising of the hot air is because of buoyancy. So the driver is buoyancy. So driver is buoyancy. Who would like to prevent this thing for you? The prevention comes from viscosity because of Stokes' law. So as soon as this parcel of hot air tries to rise, there will be viscous drag which would try to bring it down. So so one player would be viscosity, the other would be thermal diffusivity. Which will say that if I have a hot parcel of air trying to rise, then it will be exchanging heat with for it to continue rising, it would also always be hotter, it would have to be hotter than its surroundings. But if the heat diffusion is very fast, then it will lose heat very quickly and it won't be able to rise anymore. So a very good thermal diffusivity would, or thermal conductivity would prevent it from going up. So the preventive players are viscosity and thermal conductivity. So out of these, as competitors, must come a dimensionless number which will determine what happens to this system that I have talked about. That dimensionless number is what is called Rayleigh number, and that's defined by expansion coefficient times the temperature difference, and G, because gravity is the buoyancy, so this is density difference times, so you have got the buoyancy, but this is density difference, so it has to become a sort of mass, and that done through this, and then the thermal diffusivity lambda and the viscous diffusivity nu. Those are the prohibitors, so drivers at the top, prohibitors in the bottom. So this is the control number. Rayleigh number is the control number for this. So the Reynolds number, which I had in the previous discussion of homogeneous isotropic turbulence, is changed to Rayleigh number, and the critical Rayleigh number, Ra critical, is 1708 for passing from here to here. So that's so motion begins over there, and you start convecting heat from the bottom plate to the top plate. And now a set of subsequent instabilities. Remember the slide that Professor Govindan showed in the last slide that she showed yesterday, that a sequence of things which happen. So the first sequence that happens over here is that this steady pattern of rolls that sort of starts to waver. So you have these rolls now become time dependent. So this is what happens at, so somewhat higher Rayleigh number, this is what's going to happen. Then it's a nice oscillatory thing, loses oscillatory character, and finally Rayleigh still greater. You have what is called a convective turbulence. So convective turbulence, that when now your velocity field has become rather complicated. If you look at what the fluid is doing, it's no longer going around in nice wavy patterns inside, but instead you have complicated fluid motion going something or other somewhere, you know. So that's the picture. So from here, you have finally got that when you have got into this regime, it's a, but more important is the most interesting issue with this region when you have hit convective turbulence and your velocity field is going haywire, is what is happening to the temperature. So temperature, you see, the temperature, it is T2 over here and T1 over here. That's fixed. That, I mean, is a boundary condition that you can do nothing about. But you see, if you do the measurement of the temperature over here, you would find that in the middle of this cell, the temperature is, I mean, anywhere in the central region of the cell, the temperature is almost T1 plus T2 by 2 everywhere. So it's at the mean temperature of this almost everywhere. And where does the temperature variation occur? The temperature variation occurs in two regions which are adjoining the plates over here. And so here, so if you call this delta, the temperature difference as we, so there is a drop of delta by 2 over here and a drop delta by 2 over here. In between, the temperature is, and if you, it's not exactly T1 plus T2 by 2, but if that is the mean temperature, and if you look at deviations from the mean temperature, then, or rather what is done, what's more correct, is that there is a conduction. If there is only conduction, T conduction, the profile is that it is T1 plus T2 minus T1 over D times Z, that is T1 minus delta T over D times Z. So that is the conduction state profile, that there is no motion, nothing at all. The heat conduction satisfies the diffusion equation, and there is in this only Z-dependent geometry, it's a linear profile that you have. So you want to look at what is the, it's the difference from this linear profile that one is interested in. And it is, I mean, what the difference from the linear profile essentially is that you have basically a fixed temperature in the center of the cell, and deviations from that look like, I mean, so these deviations delta T from this fixed temperature, let's call it some T central, has a very sharp fall off. So probability of a deviation delta T has extremely sharp fall off as you go. So that is the phenomenological description of the turbulent state over here, and that its action, a lot of action about heat transfer is near in the boundary layers over here. And the velocity is certainly going haywire over here, but the temperature is showing a more stable behavior, the mean value with small fluctuations around mean value. Large deviations from this mean are virtually not taking place. So that's the picture. So now what is of interest? So that's the So what is of interest? Certainly this energy spectrum that we talked about, that is going to be of interest. There is going to be interest in this energy spectrum E of k. That would be there. There would be a corresponding thing, as we'll see, about the temperature fluctuation spectrum. So that, but there is a much more sort of somewhat easier in some sense, and more physical thing, which is much more easily measuring these spectra. I mean, they can primarily be measured. I mean, it's numerical work. I mean, nobody really does lab experiments are very difficult. So maybe, I mean, 1 or 2 experiments in the whole world in 10 or 20 years. That's about the rate at which good experiments go for determining spectra. But numerical stuff, I mean, is what the spectra is all about. But there is a measurable thing over here which is of vital importance. It's the heat transport. Heat transport is heat conducted plus heat convected. Now this amount of heat, all this is per unit area, per unit time. Goes without saying. Heat conducted, we all know how much that is per unit. That is lambda T, lambda times delta T over D. How much is the heat convected? Heat convected would be essentially, you would be able to calculate it by doing, let's say, a calculation of the flux. The flux would be the fluctuation in temperature times the upward velocity. So that would be a measure of how much is convected. But let's look at look at this in a slightly different manner. What is the total heat which is leaving this boundary over here? You know that the temperature difference, this thickness, this is what is called a boundary layer. And let's say the boundary layer has a thickness which is lambda, let's say dt or dB for whatever. I mean a d, but so it's a d but with a b subscript, so it's a boundary layer. So boundary layer, so how much heat is actually coming to the top of this boundary layer? The amount of heat that is coming to the top of the boundary layer is the temperature difference between these two, between this surface and this surface. The temperature difference is like delta. It's delta by 2, but that's close enough to delta. So, I mean, it's of the order of delta. So that's delta. But now, instead of this division, heat, the total heat flow, this heat transport, if you want to estimate that, that would be like lambda times delta divided by this d boundary layer. So the total amount of heat that would be transported from here to here would be the amount of heat which is reaching this surface over here, so which is the determined by the temperature gradient times the thermal conductivity, so lambda times delta T over dB. So this is, and as the boundary layer becomes thinner and thinner, the total heat transport is completely dominated by the heat convected. There is a term, a dimensionless quantity defined as Nusselt number, which is heat transported, total heat transported per unit divided by heat conducted. And so it's heat transported and this. And what is the, if you are in the limit of huge amount of all sort of being, all right, I mean, don't have to, what is the rough estimate of this? The rough estimate of this would be d divided by the d boundary layer. So d divided by the d boundary layer would be the estimate of heat transported divided by the thickness of the thickness, the distance between the plates divided by the thickness of the boundary layer. That is the measure of how much heat is transported divided by how much heat is conducted. So this is, and how much heat, what is the convection amount, then that is this minus 1. So, but as I said, it's huge. The huge amount of heat in this turbulent zone gets transmitted. So the difference between the Nusselt number is almost entirely the heat convected. So that's a small point. But it's this Nusselt number which is estimated as d over dB. So that is going to have a scale, that has a scaling behavior. Nusselt number scales as Rayleigh number to some power beta is what. And that is something which can be measured with tremendous precision, and a lot of effort has been spent over the last 15 years to get a good feeling for this exponent beta. So this is the feature which you did not have in the kind of problems that we were discussing over the last 2 days, that there is this Nusselt number, and that has a scaling law. As you increase the Rayleigh number, the amount of heat transport increases, and that does so in a characteristic fashion over here. So we would be therefore interested in two things. One would be this, and the other would be that. If it is a very high rotating system, high speed rotation, then there would be the Nusselt number would be dependent on it would be cut down because of the the rotation trying to make it two-dimensional, and the transport would be affected, and Nusselt number would have a behavior which would be scaled by the omega rotation raised to some power. And when it is a magnetic field there as well, there would be some additional things. So this opens up, this opens up a new thing to calculate and talk about, apart from the spectrum, which is always there. The great advantage of this thing is that it's directly measurable. So there are infinite number of lab groups which do this Nusselt number measurement and have a very nice idea of what this exponent has to be, which is, over here you have to depend upon heavy-duty numerics. So, yeah. Yeah.
Small delta is dependent on the total gradient.
Where is the small delta?
Boundary, how we define the boundary.
That's D sub B, yeah? Where is the small delta?
How we define the boundary, this is the boundary, say that the temperature drops by some...
almost the entire drop takes place over there. Yeah? So it is, it's half the drop because there has to be symmetric, but half the drop is like the drop. That's why it's proportional to Rayleigh number to the power beta. Rayleigh number is the total delta T. So that's the total gradient. Yeah. So Rayleigh number is the total gradient. Nusselt number is the gradient in the boundary layer. Yeah. And so the scaling behavior is that how does the boundary layer gradient depend upon the total gradient? That's, yeah. Pardon? Yeah. Huh. Sure. Yeah, absolutely. See, the picture is that in this turbulent regime, the picture is that the temperature drop essentially occurs over the boundary layers. The total temperature drop is delta by 2, delta. So there is half the drop delta by 2 over here, half the drop delta by 2 over here. Now, what is the amount of heat that gets total heat which is transported from here to here? That has to be the total heat which is leaving this surface. Now, what is the amount of heat which is leaving this surface? That is the amount of heat which is being conducted across the boundary layer to this point over here. Now, what is the amount of heat which is being conducted across this by the boundary layer, which is this dB. So therefore, yeah, so that is this lambda delta T divided by dB. And the heat conducted from top to bottom is lambda delta T divided by D. Therefore, so I'll just take 5 minutes to, write down the starting point for us for tomorrow, and then I'll stop. So I have to it's del V del T plus V dot del V equal to minus gradient P over rho. Now I have to write this rho because density is what is changing. Del square V plus gravity. So, so gravity comes in, and there is now the temperature diffusion, which is del T. This is the temperature variable anywhere. So it is V dot del acting on T equals lambda del square T. So this is the temperature diffusion. Now the temperature variable that we will use is the steady-state temperature profile, which I wrote down over there, which is T conduction and plus delta T. T conduction is known, so I want, that is a steady state conduction, and therefore if I put things, use this over here, this is del T, there is going to be delta T over here, and now over here there is going to be one additional term, because T conduction has a contribution from here. ddz is that minus delta T term, and the delta T is as is plus W delta T over D. So this finishes the heat fluctuation, temperature fluctuation business. So now what about the first one? Now first one, there is going to be, now we worked about, what about the steady state over there? The steady state over there has grad P naught over P naught equal to G vector. So that's your solution for the steady state. So this is the steady state. And once again, as before, you say that P is equal to P0 plus delta P, and rho is equal to rho 0 plus delta rho. Now do the following steps. Now do the following steps. Substitute this in over here, and the 1 over rho 0 plus delta rho, 1 over rho 0 plus delta rho is very nearly equal to 1 over rho 0 minus 1 over. This is the approximation. The dot 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 that I had written down for you, that is the approximation, that dot dot dot, that delta rho D is small enough so that I can linearize in delta rho. So that is the point. Now you keep that delta rho, write down this equation with that delta rho over there, and substitute delta rho equal to minus alpha rho times delta T. That's the local connection between the thermal fluctuation and this at the, and what you should end up with. So this is the assignment for today. Del Vi del T plus Vj I'm using I now because there is alpha, which is the expansion coefficient. Del J acting on Vi is minus I delta. So no pressure variation after I have taken that into account. That plus alpha G delta T, and this is only in the 3 direction. So alpha G delta T plus nu del square Vi. So that is what this equation should look like. Del I Vi is equal to 0, and lastly del T. Delta T plus Vj del J delta T is lambda del square delta T plus W delta T. So these are the defining equations, and so which is what you have to work out. And when rotation is on, you have to add over here 2I epsilon ijk omega j v of k. And when the magnetic field is on, then I have to have a gradient of B square and equation for B. Maybe I'll write down that at the towards the end tomorrow. So this is a good place to stop. Yeah. Got the picture? I mean, so you will be able to work out that, I'm sure, without any difficulty. Yeah.